We can do it. So he can make it, and he can miss the third, right? What else could he do?
Make it, miss it, make it.
Make it, miss it, make it. Miss, make, make.
Miss, make.
Miss, make. Miss, make, miss, right?
Make, miss.
It's two more.
Make all of them, and miss all of them.
There we go. Don't you love thinking through all that? Make all three, miss all three. That is another option for sure. So we know this guy is a 72% free throw shooter. So it says find the probability that Memphis will lose, win, or go into overtime. All right, so what does it mean for them to win? He has to make all three of them to win, right? So then your question is, does it matter if he makes the first one, does that affect the next one? Next shot that he makes? No, it doesn't, right? Just because he made the first doesn't guarantee he's going to make the second, right? Or the third, and vice versa. So to win, he has to get all three. So it's 72% chance he makes that first throw times a 0.72 for the second and a 0.72 for the third, which we could write that as 0.72 cubed. That makes sense, everybody? Those are independent of each other. That's why we can multiply them. So when you do all that, you get 0.373. Okay, so what would have to happen for them to lose the game? Miss two?
Yeah, he has to miss two.
Everybody clear on that? He has to miss two and get one, right? So if he gets one, we know there's a 72% chance of getting that one. What's the probability that he misses, though? Missing?
No, it's
0.28, right? Remember the complement thing we did? So to get it is 72% chance, which means there's a 0.28 or 28% chance that he misses. But we need two misses. And you could write that as 0.28 squared. Yep. And when I do the math on that, I get 0.022. Now, but if you look back at our values up here, how many different ways did we have miss two and get one?
4 or 3.
There's three of them, right?
4 ways to lose.
So there's three of those. So in order to accommodate for that, we have to take this and multiply it by 3 because there's 3 ways that combination can happen. And that comes out to be what did I do wrong here? Oh, wait. Did we do that wrong? To lose means he needs to miss all 3, doesn't he?
No, they're only down by 2.
He misses 2 and only gets 1 point. He's still down by 1.
He missed but was fouled. They're down by 2. But I thought to lose they had to have 3 misses and they'd go to overtime where they have 2.
No, they only have, if they make 2, then they go to overtime.
Yeah.
Did we read that wrong? They trailed by 2 points.
Maybe this is 2. It only makes 1. That's
This is backwards from my notes though, so I'm confused what I did here. 3 misses. Oh, okay. I put the wrong value here. That's what it is. This one is not 0.22. This is 0.56. Sorry.
So we were about
So 3 ways that can happen. So I get 0.169. Now another way they could lose though is what? To miss all 3?
yeah.
Does that make sense? Okay. Miss all 3, so that would be 0.28 cubed, right? That's the one that comes out to 0.022.
I see.
Now, so there's 2 scenarios in which they can lose, and there's only way you miss all 3, right? You miss all 3. So the total probability for losing would be 0.169 plus 0.022, and this gets a little bit crazy, but we'll be fine. We'll add those in a second. All right, and then overtime would be what? What do we say?
Make 2.
2 makes. Excuse me. Excuse me. Alrighty. And I get 0.145. Now, how many ways do we have 2 makes and 1 miss?
3.
There was 3 of those up here in our combinations, right? So we have to multiply that by 3, and I get 0.435. Now, don't worry. When you do problems like this, it's not going to be this convoluted, I promise. Okay? This example is kind of long. But it kind of gets you the idea of why do we have to multiply by 3? Well, because there's 3 ways it could happen, right? Okay, so prior to watching each shot, it says calculate the probability that Memphis wins the game in regulation, loses, or sends it into overtime. So, to win the game means that he makes all 3 shots. We already said that, right? So that's this probability. So 0.373. To lose the game, that is the addition of those 2 possibilities, 0.169 plus 0.022, and that adds up to 0.191. And the overtime, we said, is 0.435, right? That's what we just did. All right, so let's say, all right, he makes the first free throw. So now the score is 75-74. He has 2 free throws left. What's the probability he's going to win? What has to happen for him to win? He has to make the next 2. So 0.72 squared, right? Gives me 0.5184. He has to make those 2. What about to lose at this point? He has to miss both, right? So this would be 0.28 squared, which gives me 0.0789. And then overtime would be a make and a miss, right? But there's 2 ways that can happen. He can make the first, miss it, or he can miss the first and then make it. So we would have to multiply by 2. So make it, miss it, times 2, because there's 2 ways. .4082. All right. All right, let's say he misses this one. He misses the second one. So the score is still 74-75. He only has 1 shot left. What's the probability they can win? 0. Can't happen, can it? Because he has to have more than 75. but he only has one shot left. Probability they'll lose. What has to happen for them to lose? They has to miss. So what's the probability of a miss?
0.28.
Yep. It's just 0.28. Easy enough, right? And the probability of an overtime? 0.72. So you can see it depends on the previous result, doesn't it? Okay, so Washington is a 40-point free throw shooter, not 72%. So now, do you think it was smart for them to foul him?
The Washington guy or the Memphis guy?
Washington's the name of
Oh,
it.
wow.
Washington is the Memphis guy.
I was thinking it was a different team for some reason. See, it was
I
too.
was so confused.
By what? Huh?
I know, I thought you were talking about like
Washington was like a different team.
No, Darius Washington's the player from Memphis.
That's right.
Sorry. So we were building all these probabilities based on him being a 72% free throw shooter. But in reality, it's 40%. So what do you think?
I think it's what if he made it and then got fouled after and he had 3 chances?
What if, right? Okay. We could do the thing all day. Here's what you need to know. I'm going to break this down for you because that was kind of in the weeds a little bit number-wise. So what is it you need to know about this? Well, what we were looking at was what you call a binomial probability scenario. Okay? And so we're going to look at what are the criteria that make it binomial. And there's a formula that takes a shortcut to all that work we just did. Okay? Trust the process. I know there's a lot of letters. It looks kind of scary, but it's not that bad. I promise. Okay? All right, so what has to be true of the scenario that you read about for it to be binomial, which means you can use the formula? First thing is it has to be binary. Binary means 2 options, success or failure in this case. So in that example, the success is making the free throw, the failure is missing the free throw, right? All right, then the next thing has to be true is they have to be independent. So this is why each free throw is independent of each other, right? Just because I made the first doesn't mean I'm making the second. N is number of trials. So it's a fixed number. How many free throws did he have? 3, right? If he had unlimited, then this would not be binomial. You have to have a set number of trials for this to work. And then this last one is for same probability of a success for each trial, where they give you that. And that goes hand in hand with being independent. If they're not independent, then they don't have the same probability, okay? So we run it, I call it the BINS test, B-I-N-S. Binomial, independent, number of trials, same probability. So you've mentally checklist that, and then you know, okay, this is binomial. I can use this formula. I can use this little trick in my calculator. All is well, right? So here's the formula. It looks really gnarly, doesn't it? It's not. It's really not that bad. So probability that x equals k. K is just however many successes we want. That's all it is, okay? So I'm just going to call it number of successes when we read the question. All right? N is the number of trials. And P is the probability of a success. Now, we did this, you just didn't know it. Remember how we did like 0.72 times to the third power to make all 3? That's this piece right here. 1 minus P is how we came up with the 0.28. The complement thing, right? And we said like, okay, if he makes 2, he misses 1, right? Well, guess what? 3 minus 2 is 1. So we were already doing that logically. This is just putting it on paper. What looks weird is this piece right here. All right, this piece of the puzzle is going to keep you from having to think through all the combinations of how many ways can you miss? How many ways can you make it, right? The miss, make, miss thing. That's what this piece does right here for you. It is a built-in formula in your calculator. You don't ever have to do it. You just know how to enter it. That's all. So notice it's based on n, number of trials, and k, number of successes desired, right? So we plug in, the calculator will say, okay, what's n, what's k, what's the probability of a success, and it'll spit out the answer for you. What you have to know how to do, because TW likes to go old school in the formula, is know what the formula is saying, all right? So this is the piece, might be weird. How many ways, how many combinations can happen like that? That is the piece that you need to, that might be unfamiliar. P is the probability of success, K is the desired number of successes, and then the rest of this is like the complement stuff. All right, so let's walk through an example of this, and I think it'll be better because the basketball one kind of gets tedious. All right. All right. For each of the following, determine whether or not the given random variable is binomial. So we're doing the Benz test on these. That's all we're doing. Okay? We're not even calculating anything. You play a game of whack-a-mole. From playing the game in the past, you know whack-a-mole, right? Yeah. Okay. You know that you have an 80% probability of whacking the mole before it drops back in the hole. The mole pops up randomly, and your ability to whack any particular mole is not affected by whether or not you whacked the previous. There's 20 moles to be whacked during one round of the game. X is the number of moles that you're able to whack. All right. So let's run it through. B, binary. What are my two outcomes here? Hit it or you don't, right? So a success means I hit it. A failure means I missed. Okay, there's only two options here, right? So the B, the binary criteria has been satisfied. I, independent. Each whack depends on each other? No, they're independent, and they told us that, right? It says your ability to whack any particular mole is not affected by whether or not you whacked the previous. So each independent. Yup. N is the number of whacks. Do we know how many whacks? There's 20. So N is equal to 20 in this example. So we have a set number of trials. And then S is the probability of a success. What is that? 80%. So do I have a check on each of these criteria? Yeah. Easy enough. So this is a binomial situation. All right? So let's, for funsies, let's see, okay, what's the probability I get, how many successes do you want to get out of 20? That you get all 20? You want to do all 20? Let's do less than 20 because I need a less than 20. 19? Okay, sure, right. All right, let's do 19. Now, what I want to do is just show you what that formula would look like, and then how the heck are we putting this in our calculators? All right, so remember the first thing in that formula is that C thing? Okay, so I have to put N first. N is 20, right? So I'm going to do 20C, and I want 19 successes. Then I do the probability of a success, which we know is 80%. And how many successes did we want? 19. So I don't want to multiply that out 19 times. I want my calculator to do it. So if I have 19 successes, how many failures do I have? 1. And then what's the probability of a failure? 0.2. So this is the way the equation would be written out. You are not putting it in your calculator like this because I don't want you to have to mess with all the keystrokes for that combination. However, there is a function in your calculator, and it looks like this. It says binomial PDF. So let me show you where that is. If you pull out your calculators, as I get mine out, All right, you're going to go to, do you see the VARS button, VARS? It's right under, it's right by the, it's going to, down the left from the arrows. See VARS? You don't want VARS. You want distribution, which is the second menu. So you're going to hit second VARS. And there's all this cryptic looking stuff, right? So I'm going to scroll through that, and you can scroll down or up, it doesn't matter, until you see binomial PDF. Second VARS. Help your neighbor if your neighbor can't find it. Second VARS. Go all the way till you see binomial PDF and hit enter. And then yours is probably fancier than mine because it may, does it say N? Does it give you the prompt N?
Trials.
Oh, it says trials. Okay. You're even fancier than mine. Mine just says N, so I have to know that N means trials. Okay? So yours tells you, give me trials, gives me X. X is how many successes. P is your probability. Everybody find it? Ava, did you find it? Yeah? Okay. So for me, I have to put in commas. It's wonderful. So I have to do 20, 0, 0.8, and I want 19 successes. All right? So mine looks a little different than yours. Everybody get there? And you hit enter, and boom, there's your answer. Can we handle that? Now, as far as work, this is the work you're showing me, is the equation written out, but the calculator's doing the math. Can we handle it? All right, cool. Now, let's go back and look at these other scenarios really quick. Next, you play skee ball. You know that you have 10% probability of getting a given ball in the 10,000 point hole. Let y equal the number of balls you have to roll until you get one in that hole. All right, so let's think. Is this binary? What is a success here? 10,000K, make it, right? A failure is to miss it. Independent. Is each roll of the ball independent of the previous? Yep. N, do we have a set number of rolls? We don't, does it? No, because it says y is the number of balls you have to roll until you get, right? So we don't have a set number of rolls, so this is where it fails, the Benz test. This is not binomial. We cannot use that formula. We're done with the question. Make sense? Let's look lastly at this one, number 2. Now you play a game called Tsunami Duck Pond. Okay. In Tsunami Duck Pond, there's 100 ducks that get pummeled by tidal waves. You have to reach your hand into the tsunami and select a duck. If there is a star on the bottom of the duck, you win. The game claims to have 20 ducks with stars among the 100. After each round, you place the duck back in the tumultuous water. Let W equal the number of times you win if you play the game 10 times. All right, let's see if it's binomial. So, what's a success here? A star on the duck, right? A failure is no star. Independent. Does what you draw each time depend on the previous draw? No. When I draw one out, I have to put it back in, right? And then it reshuffles, the tsunami hits again, and then they pull up. Yeah, so but you're only drawing one, right? Isn't that right? You reach in and you select a duck, and then you check to see if you won, and then you put it back in and it shuffles again. That makes sense? So because you're replacing it, that probability is not changing. Does that make sense? Okay, so because replacement, this is independent. Now, if it hadn't told us that we were replacing it, then you're right, it would be a problem, but it's not. Okay, so N is how many are we choosing? How many times are we playing? 10 times. And what's the probability of getting a star? 0.2 because it's 20% chance, right? All right. So, does it pass? Yes, it passes. So find the probability that you win exactly 3 times. So let's see if you can do this. Probability that x equals 3. I'll give you a second. See if you can set up the equation and do it in your calculators and see how we did. Caden, do you have that on your calculator?
I think so.
Well, that's the one part of the equation. Does it have the binomial thing in there? I mean, you can hand type it in, I guess. But, problem is when you do the NCR thing, you have to put in the 10 first and then the NCR and the 3. It's complicated. Did I give you a calculator?
Yeah, it's on my house.
Oh, okay. Okay. There's an app on your phone you can do if you want. It's called Calculate 84. It's free. It does it. Okay. All right. Ready to check it? Let's see. Did you get 0.201? Yeah? Were you successful in getting that equation written out? Not so bad, right? No? Okay. Now, that's binomial probabilities. Now, are they always this easy? No. Probably not, because you know how math is. Probably not. But we will work through this, all right? So, I'm going to switch gears for a second.